I wanted to make a video of this problem because I thought it was a good example of using our new relationship that the sum of the torques acting on a rigid body object is equal to the moment of inertia times the angular acceleration. So the idea is that if you drop a roll of toilet paper but you're hanging on to the edge of the first sheet, it kind of unrolls as it falls. And so there's a torque produced by the fact that you're holding that sheet that allows it to roll or rotate as it falls. And we want to look and see how long does it take for it to fall a particular distance. In this case, we're told that it's going to fall 0.73 meters. I wanted to compare it. I think it would be interesting to think about what if we just dropped it? Instead of unrolling the toilet paper roll, what if we just had it in our hand, we let it go, and it fell through free fall? Let's look at how long it would take in that situation, because then our answer when we look at it unrolling will mean more to do that comparison. So if it fell through free fall, we're looking at our kinematic equation for free fall, where in this case our y naught would be equal to the 0.73, and y is when it hits the ground, that's 0. So we have 0 equals 0.73. We're just going to drop it so it has no initial velocity, and then minus 1/2 9.81 t squared. So let's solve for the amount of time it takes to fall through free fall. So I did the rearranging there. Hopefully you can follow that algebra. And it takes 0.386 seconds to fall. So that's something that we can remember. Now we're going to use this. Now we're going to look at the forces acting on the toilet roll and also the torques. So first of all, we have forces in the y direction equal the mass times the acceleration in the y direction. And so we expect the acceleration to be downward, obviously. There's a tension in the end of the roll, the sheet that we're holding, that's acting up. And then we have the weight of the toilet roll. And so that's minus mg. And then we have minus m times a. So that is the expression we have. So we're just going to, I'm going to cheat. I know I'm going to need an expression for tension, so I'm going to rearrange this equation. I have mg minus ma. So I'm going to use this in a little bit later. First, now I'm going to look at torques and the moment of inertia times the acceleration. Now there's only one torque acting on this roll. The tension as we hold the sheet provides a torque because it's off center of the very center of the roll. The force of gravity acts at that center, and so if we calculated the torque, the distance would be 0. So it doesn't produce a torque. It doesn't cause the toilet paper roll to roll or to rotate. So we only have T times R, so that tension times the radius. And this case is treating the toilet paper roll as like a hollow cylinder. So it has two radii, the outer radius and the inner radius. So for the torque, the distance from the center of rotation is R2, the outer radius. And this is also the moment of inertia of this hollow cylinder is one that we're not as familiar with. where it's 1/2 m, and we have the inner radius squared plus the outer radius squared. And then times alpha. They have alpha in this picture drawn counterclockwise, but this tension is going to cause it to rotate clockwise, so I'm just going to stick with that, and that's why these two signs on the left-hand side and the right-hand side agree with each other, because the torque that causes the angular acceleration, they should be the same sign. So you can see here that there's a place to put the tension in. And we can do that substitution. And in order, sorry. Let me fix that. And now I also want to write the acceleration in terms of the linear acceleration, and so that angular acceleration is going to be a over r2. Sorry, it's not r squared, it's r sub 2. All right, that means then this expression is, everything is in terms of a. Now I'm going to rearrange this equation, so I have terms that involve acceleration are all on the right-hand side, and everything else will go to the left-hand side. We don't have too much. We have mg on the left-hand side times r2, and then I have 1/2 r1 squared plus r2 squared times a over r2, and then plus m a r2. I forgot the m somewhere. The m got lost as I went down, so the reason I wanted to put that m in is because we have an m in every term and we can cancel this out. So I'm gonna just kind of try to go over here. So I have g r2 equals, now I'm going to factor out the a. It's going to be kind of messy, but it's okay. And then I'm going to divide through by an r2. So I have that. All right, I'm gonna continue this on the other page because it's getting kind of full. So let me rewrite what I have. Yeah. I'm solving for the acceleration, and I had r1 squared plus r2 squared divided by 2r2 squared plus 1 times a. I'm just going back to double check that's what I had. So I can simplify this a little bit. So I'm looking to figure out what the acceleration of this toilet paper roll is now. R1 is 0.027, R2 is 0.061. If I put these values into this expression, I would get G is equal to 1.59 times A. So if I solve for A, it's 9.81 divided by 1.59. So you can see that we've slowed down the acceleration here. It's going to be 6.14 meters per second squared. Let's put this back into our expression to see how long it takes this to fall. This is A, not G. So 0 equals 0.73 minus 1/2 times 6.14 t squared. So we have a new acceleration. Our t now is 0.488 seconds. Our original time was 0.38. Seconds. And it's just kind of interesting to see that the time that it takes it to fall is slower because of the fact that it's unrolling as it's falling.